TON 618 does not draw astronomers' attention only because it is large. The difficult part lies in the moment when its light left. The light from this quasar has taken more than 10 billion years to reach telescopes on Earth. That means we are not seeing TON 618 as it exists right now. We are looking at a very old record, from when the universe was far younger than it is today. In that record, estimates suggest that the central black hole of TON 618 may be more than 60 billion times the mass of the Sun. From here, the question is no longer how large it is, but how it had enough time to grow that large. A black hole does not shine on its own to reveal its position. It's only recognized through the matter heating up and glowing around it. The faint blue point of light that once appeared in observational data was gradually identified as a quasar, shining because matter was falling into the supermassive black hole at its center. If current mass models are correct, TON 618 should not be seen merely as a record holder. It raises a harder question. What conditions did the early universe create that allowed a black hole to grow faster than ordinary growth models can easily explain? Before TON 618 was mentioned alongside the largest black holes ever known, it did not appear as a giant structure in the sky. It was only a faint blue point of light in observational data. In 1957, at the Tonantzintla Observatory in Mexico, astronomers recorded this light source during a sky survey. In the images from that time, TON 618 did not reveal an accretion disk, did not show a clear galactic structure, and also showed no visual sign that behind that point of light was an enormous source of energy. With the equipment of that era, it could have been mixed in with countless other faint light sources in the sky. The turning point did not come from a sharper image. It came from the spectrum. When the light of TON 618 was separated by wavelength, the signs in the spectrum began to show that it was not a nearby light source. This was not an ordinary star in the Milky Way. Its light was strongly redshifted, a sign that the source lay far beyond the Milky Way. If a source that distant was still bright enough to be recorded, the energy behind it could not have come from a single star. TON 618 was gradually recognized as a quasar, the active core of a distant galaxy, where matter falls into the central black hole and releases extremely powerful energy. TON 618 was not identified by directly seeing the black hole at its center. That black hole has no bright surface, no clear outline, and does not emit light on its own. The part that can be observed lies in the region around it. That signal comes from matter being heated before it moves toward the boundary from which there is no way back. A small point of light on the sky map became the trace of a process on a galactic scale. And from there, the question about TON 618 changed. It no longer stopped at what that point of light was in the sky. What at the center of a distant galaxy could create a light source powerful enough that it took more than 10 billion years to reach Earth? TON 618 is easy to misunderstand because the black hole at its center does not appear as an object that can be seen directly. A black hole has no glowing surface. Inside the event horizon, light cannot escape. If we consider only the black hole itself, it does not emit a light signal on its own to be identified from afar. TON 618 is recognized not from the darkest part, but from the glowing region of matter around it. At the core of a distant galaxy, gas and dust do not fall straight into the black hole along a simple path. They orbit the black hole, become compressed, collide, gradually lose energy, and heat up. From the outside, that process forms an extremely hot accretion disk surrounding the black hole. The light of the quasar does not come from inside the black hole. It comes from matter just before that matter crosses the final boundary. The closer matter falls toward the black hole, the faster it moves, the hotter it becomes, and the more radiation it emits across many wavelengths, from visible light to ultraviolet light and X-rays. When the central black hole is large enough and the supply of matter around it is abundant enough, the galactic core can shine brighter than the entire rest of the galaxy that contains it. With TON 618, what was recorded first was not the black hole, but the quasar. From that light, astronomers infer that there must be a supermassive black hole at the center controlling the accretion process. An image may only show a point of light, but a spectrum can reveal distance, energy level, and signs of matter moving extremely fast near the galactic core. So the paradox of TON 618 is not that the black hole shines. The paradox lies in the fact that a region that does not allow light to escape can make the area around it shine so intensely that it outshines its host galaxy. The initially cold gas is transformed into hot plasma, moving rapidly within the accretion disk and releasing energy before part of it falls into the black hole. Before part of the matter crosses the final boundary, it has already released a signal strong enough to still be recorded after a journey lasting billions of years. That energy source requires a supermassive black hole at the center to sustain the accretion process. Matter is falling into a region that cannot be seen directly, but the matter outside that boundary reveals the presence of the black hole. If the region around TON 618 can emit a signal that powerful, the black hole controlling that process must have an enormous mass. From here, the story shifts from the brightness of the quasar to what lies behind it, the mass of the central black hole. The light of TON 618 does not only tell us that it is far away, it tells us that we are looking into the past. When telescopes on Earth record this quasar, they are not seeing its current state. They are receiving light that left its source more than 10 billion years ago. That light departed from a time before the solar system was born, when the universe was very different from what it is today. With a closer black hole, astronomers can track the motion of stars, gas, and dust in greater detail. With TON 618, the data comes from light that has been stretched by the expansion of space. What remains is the spectrum, brightness, redshift, and the models used to infer the black hole at the center. The distance of TON 618 is also where many people easily misunderstand it. More than 10 billion years is the amount of time the light has traveled. During that time, the universe has continued to expand, so the present-day distance to the region of space containing TON 618 may be much greater than the number describing how long its light has traveled to reach us. The two numbers do not contradict each other. One number describes the journey of the light, while the other describes distance in an expanding universe. When astronomers talk about the brightness, energy, or mass of the central black hole, they are state of the system at the moment the light left. In the billions of years since then, the quasar may have weakened, its gas supply may have run low, or the central black hole may have grown larger. So the mass of TON 618 has to be placed in the correct observational moment. If current estimates are correct, the central black hole had already reached a scale of more than 60 billion times the mass of the Sun during a very distant period in the history of the universe. It is the trace of a structure that was already enormous very early on. The problem no longer lies in its individual size. The question shifts from mass to growth rate. The signal from this quasar carries traces of a period when large galaxies and black holes were still maturing. A signal that could leave its source more than 10 billion years ago and still be recorded clearly cannot come from an ordinary source. The brightness of TON 618 is the next layer of data that needs to be examined more carefully. When the light of TON 618 takes more than 10 billion years to reach Earth, what allows it to still be recorded is not just distance. The original source must have been extremely powerful. If it had been weaker, that signal would have sunk into the cosmic background long before it reached our telescopes. The main light of TON 618 does not come from the entire galaxy, but from the active core at its center. That is a region far smaller than the host galaxy, but it can outshine the rest of the galaxy's light. In a normal galaxy, light is distributed across stars, gas, and dust. With a powerful quasar, the core can overwhelm almost that entire picture. In observational images, TON 618 may appear as only a small point, but in the data, that small point carries the signature of an active galactic core surrounding a supermassive black hole. This is the contrast that makes TON 618 difficult to grasp with the naked eye. The image shows very little. The data points to an enormous source of energy. If a quasar like TON 618 were much closer, the night sky would no longer look like the sky humans are familiar with. This is only a comparison of brightness, not a threat to Earth. But it shows the intensity of the source. It would not look like a star that was simply brighter than normal. It would become a light source dominating the sky. That brightness is not the steady light of a star. It is the sign of a galactic core actively operating around the central black hole. The spectrum shows that TON 618 is very far away. Its intensity shows that the core cannot be an ordinary structure. A small point of light in an image begins to carry the weight of an entire active galaxy. But brightness is still only an external sign. If the core of TON 618 can release that much energy, the black hole controlling that process must have an enormous mass. The next question lies in the mass of this central black hole. The brightness of TON 618 is only the first layer. The part that makes the story more serious lies in the mass inferred for the central black hole. The estimates often mentioned place this black hole at more than 60 billion times the mass of the Sun. One commonly cited estimate puts that number near 66 billion times the mass of the Sun. Even when expressed carefully, that scale still places TON 618 among the most extremely massive black holes ever known. But this number should not be understood as a direct weighing. The mass of TON 618 is inferred from the spectrum, from the motion of matter near the galactic core, and from models that connect those signals to the gravity of the black hole. The mass is the result drawn from that data, so the more accurate way to say it is that current data points to a central black hole with an estimated mass of more than 60 billion solar masses. TON 618 does not need any added layer of exaggeration. The possibility alone that a black hole could reach a mass of more than 60 billion solar masses is enough to make every familiar scale feel too small. The Sun is used here as a unit of mass. One Sun is already the gravitational center of the entire solar system. But with TON 618, that unit has to be multiplied more than 60 billion times to approach the scale inferred for the central black hole. From here, familiar measurements begin to feel too small. With a black hole, Mass is not just a number on paper. It expands the region of space where light can no longer escape. That boundary is called the event horizon. With TON 618, if current estimates are correct, its event horizon reaches a scale of hundreds of billions of kilometers. The comparison with the solar system only helps place that scale into an image that is easier to grasp. From Mercury to Neptune, light already takes many hours to cross the scale of the planetary orbits. But beside the dark region of TON 618, that scale shrinks into a small unit. This scale is even harder to grasp because a black hole has no surface for the human eye to hold onto. The event horizon is a physical boundary, not a glowing wall. Outside that boundary, light can still escape if it travels in the right direction. Inside it, every future path leads deeper into the black hole. The important part lies in the range where its gravity controls light and matter. A dark region so large that light would need weeks to cross its scale has already gone far beyond every familiar sense of space on Earth. Behind that signal is a mass that makes familiar distances in the solar system seem small. But size is not the final stopping point. A black hole on this scale also changes how light and time are observed near it. At the scale of TON 618, familiar distances no longer help humans grasp the problem. Even light leaving the region around it is altered by the gravitational field before it can reach an observer. Far from a black hole, a ray of light can still be imagined as following a relatively straight path. Near a strong gravitational field, that path begins to bend. Space around the black hole is curved, and the path of light is curved along with it. A signal passing close to the black hole can change direction. Some light from behind the black hole can also be bent toward the observer. The image near the event horizon, therefore, does not resemble the way the human eye sees an ordinary object. This does not mean the black hole has a surface that reflects light. Inside the event horizon, no signal can escape. Everything that can still be recorded comes from matter outside that boundary. There, the signal can be deflected, shifted in color, or weakened before it leaves the region of strong gravity. With TON 618, if the mass estimates are correct, that region of influence extends across an enormous scale. Mass does not simply create a wider shadow, it reshapes the surrounding space, making the path of light lose its familiar simplicity. Time also changes within that gravitational region. According to general relativity, time near a strong gravitational field passes differently from time farther away. To a distant observer, processes near the event horizon can appear to slow down. A signal emitted from deep within the gravitational field also loses energy as it escapes. It shifts toward longer wavelengths, creating the phenomenon known as gravitational redshift. These effects still belong to the region outside the event horizon, where data can still escape. Inside that boundary, the story must stop. No signal returns to provide direct data. So the certain part does not lie in what is happening inside TON 618. The certain part lies in the region outside it, where light and time have already been bent away from the way we are used to measuring them. A planet has a surface. A star has a glowing layer of gas. A galaxy has stars, dust, and gas. A black hole is different. It is recognized mainly through its influence on the surrounding environment. It is present through what it does to nearby matter, light, and time. The closer we move toward the event horizon in the model, the less it feels like we are observing an object directly. It is more like a journey to the outer edge of observational data. So the value of TON 618 does not stop at its mass. It shows a region of space where measurements have to operate near the edge of what can still be observed. When that limit is reached, the question is no longer only how light is bent. The larger problem lies in the past of this black hole itself. How could a structure like this have grown to such a scale when its light comes from a very distant period in the history of the universe? After brightness, distance, and size, the hardest part of TON 618 finally appears. A black hole more than 60 billion times the mass of the Sun is already enough to put every familiar scale at a disadvantage. But a black hole reaching that level during a very distant period in the history of the universe raises a different problem. TON 618 does not only have to be large, it has to have grown large fast enough. In current models, black holes do not begin with enormous mass. They need an initial seed. From that seed, a black hole gains mass by accreting gas, pulling matter toward the center of a galaxy, or merging with other black holes as galaxies evolve. With TON 618, speed is the part that creates the pressure. If the initial seed is too small, it needs a great deal of time to grow to a supermassive level. A seed born from the remnant of a massive star can weigh many times more than the Sun. But going from tens or hundreds of solar masses to tens of billions is an extremely long path of growth. It does not only need matter, it needs matter to fall in at a high rate for long enough. But a black hole cannot accrete matter without running into limits. When gas falls close to a black hole, it releases powerful radiation. That radiation can push the surrounding matter back outward, slowing the accretion process. The very energy produced during accretion can slow that process down. Growth models have to balance two opposing forces. Gravity pulls matter inward, while radiation from the accretion region can push matter outward. For extremely massive black holes in the distant universe, this balance becomes a strict constraint. One possible explanation is that the initial seed of TON 618 may have been much larger than an ordinary stellar remnant. In some models, giant primordial gas clouds in the young universe can collapse directly into black holes, weighing tens of thousands or hundreds of thousands of times the mass of the Sun. If that happened, the black hole would not need to start from a seed that was too small. It would begin from a larger baseline mass, but direct collapse requires very narrow conditions. A large gas cloud usually tends to break into many smaller parts and form stars. To collapse directly into a large black hole, the surrounding environment must be very special. The gas must not fragment too early, cooling must be limited, and the flow of matter must continue pouring into the collapsing core. Even one change in the initial conditions could send the outcome in a different direction. Another possibility is that TON 618 once went through periods of very strong accretion, when gas flowed toward the galactic core at high density and helped the black hole gain mass faster than usual. This could happen in gas-rich young galaxies, where the structure was not yet stable and streams of matter were still flowing strongly toward the center. But strong accretion brings its own problem. How could that gas supply be maintained long enough without being pushed back outward by energy from the quasar? The more active a black hole becomes, the more capable it is of heating and pushing gas away from the region near it. If the gas supply is cut off too early, the growth rate drops. To reach a mass like TON 618, the surrounding environment must be both rich in gas and able to keep that gas flowing inward for a very long time. Mergers between black holes may also play a role. As galaxies grow and collide, the black holes at their centers can move closer together, lose orbital energy, and eventually merge into a larger black hole. This process helps increase mass step by step. But mergers do not solve the entire problem on their own. They require enough collisions, enough time, and the right conditions for the black holes to truly reach the stage of becoming one. So TON 618 does not force science to abandon current models. But it pushes those models into a region that is harder to explain. If the initial seed was small, accretion must have been extremely efficient. If the initial seed was large, the young universe must have created special conditions for direct collapse. If mergers played a major role, the history of the host galaxy must have been dense enough and active enough. Each explanation requires its own conditions, and none of them closes the entire problem by itself. TON 618 does not stop at a number for mass. It forces people to ask about the process that created that number. How large was its first seed? How long did the gas flow feed it? How much did energy from the quasar slow its growth? And why, after those limits, did this system still reach the scale inferred from the data? Seen this way, TON 618 no longer looks like a single record. It looks like a trace from the era when the universe was forming its first large structures. That was a time when gas, young galaxies, and early black holes may have created growth pathways that humans still have not fully described. The biggest question is what conditions allowed a black hole like this to grow large in time? As long as that question remains open, TON 618 becomes a test of how humans understand the formation of the largest black holes in the history of the universe. After examining how it formed and grew, TON 618 has another role. It becomes a background source for reading what lies between it and Earth. Because it is very distant and very bright, the signal from TON 618 can carry traces of regions of matter along its path. When light leaves TON 618, it does not pass through a completely empty space. On its way to Earth, it travels through thin gas between galaxies, scattered matter, and structures that are still forming. Part of the signal is absorbed at certain wavelengths. Another part is weakened or stretched by the expansion of space. Those changes are not meaningless noise, they are traces. When astronomers analyze the spectrum of a distant quasar, they are not only reading the source itself, they are also reading the absorption lines that gas along the way leaves in the signal. Each absorption line can suggest the type of atom present, the location of the gas, and the state of the intergalactic environment at that time. Because of this, a very distant background source can help astronomers recognize layers of matter too faint to shine clearly on their own. With TON 618, that role matters because its light comes from a very early period in the history of the universe. The data from it does not stop at the active galactic core. It also opens information about the environment surrounding that galactic core. There is gas there, chemical composition, intergalactic matter, and traces of young galaxies changing the environment around them. Those things do not appear as a clear image. They have to be read indirectly. The signal of TON 618 leaves its source and then passes through many layers of matter before reaching a telescope. So it is studied in two directions at the same time. It is the sign of an extremely massive black hole, and it is also a bright background that helps reveal fainter layers of matter in front of it. Astronomers do not see the early universe as a complete scene. They receive scattered signals, separate them by wavelength, compare them with models, and then reconstruct each part of the picture. Every conclusion depends on the accuracy of the data and on how the model explains the spectral lines. So TON 618 does not explain the entire early period of the universe by itself. It provides a rare line of sight into a very distant stage of the universe. In astronomy, distant and extremely bright objects are often used as reference points. They help measure distance, test expansion, identify intergalactic gas, and track how matter changes over time. With TON 618, the same signal both leads to questions about the central black hole and opens a way to read the environment around it in the distant past. So TON 618 is not only about matter falling into a black hole, it also preserves information about the environment that its light passed through. Near the central black hole, matter can approach the boundary of no return. But the signal escaping from the region outside, it carries information throughout its journey to Earth. Within that signal are traces of the black hole, the host galaxy, the gas between galaxies, and a stage of the universe when the first large structures were forming. Seen this way, TON 618 no longer feels like a name on a list of giant black holes. It becomes an observational anchor. It is where questions about mass, growth, and the cosmic environment meet within the same signal. The remaining question lies in the limit that this signal sets. If TON 618 is both an extremely massive black hole and a marker from the distant universe, what is it telling us about the limits in how we understand the growth of the first structures? In the end, TON 618 does not leave behind a neat answer. It leaves behind a chain of traces from quasar light, from the inferred mass, and from the question of how a black hole could grow so quickly in the early universe. TON 618 is not only memorable because of its enormous scale, it is memorable because of the gap that scale opens. Current data shows a central black hole that may be more than 60 billion times the mass of the Sun, but the true history that brought it to that level has not yet been closed with a single answer. Perhaps its starting point was already very large. Perhaps it was once fed by extremely powerful streams of matter. Perhaps its host galaxy went through a history more complex than the old light still allows us to see. But that is exactly what makes TON 618 important. It is not only a record of size, it is a limit in how humans understand the growth of the first black holes. Thank you for staying with Astrexo until the end of this journey. If this video helped you see TON 618 as an open question from the early universe, leave a comment below. Don't forget to like, share, and subscribe to Astrexo to keep following the next journeys.